Section 2.1, Vectors in the Plane. We're going to start by talking about what a vector is, as well as how to represent vectors visually and with vector notation. And then we'll do a few small manipulations on vectors, specifically vectors in the plane. So we're going to start with 2D vectors today, and then we'll move on to vectors in 3 dimensions later. One way to represent a vector is by using a directed line segment or an arrow. So on the screen here, I have a number of different vectors for you to visualize. There's a few key points to a vector that we need to make sure that we understand. So let's start with the initial point. That's the point on the directed line segment that does not have an arrow. So every vector with an arrow representation will have an initial point. We'll also have a terminal point. That's the tip of the arrow. There's 2 other things that all vectors have, even if they aren't represented as a line segment. All vectors will have a magnitude. In the example of a directed line segment, the magnitude of the vector is represented as the length of the segment. And then lastly, direction. When we use a directed line segment to represent direction, we can just follow with our eyes, starting from the initial point and extending towards the terminal point. We just follow with our eyes to see the direction. But we could use an angle. For example, we could say that this vector makes maybe like a 30 degree with the x-axis, or it's 30 degrees north of east, for example. But these are the basics. For a plane vector, that's a vector with 2 dimensions, it will have all 4 of these things: an initial point, a terminal point, the magnitude, and then the direction. When 2 vectors have the same length and direction, or same magnitude and direction, we call them equivalent vectors. Now, we're not saying equal, we're saying equivalent. And the reason why we're not saying equal is because the vectors could be in different places, but still have the same length and direction, so they can be equivalent. So looking at the different vectors we have here on the screen, you might notice that some of these are the same length. For example, the gold vector, the red vector, the blue vector, the green vector. Those all look like they could be the same length. However, they're not pointing in the same directions. The initial point for the blue vector is down here, and on the red vector, that's the terminal point. So these are actually pointing in opposite directions. The blue and the red point opposite of each other. They might have the same length or magnitude, but they have exactly opposite directions. The blue and the green vector, they might be the same length, but they're not parallel to each other, meaning I can tell that they're not pointing in the same direction. The white vector, if I compare that to the blue vector, or any of the other vectors on the screen, I can tell that it's not the same length. The white vector is too short. So that really only leaves the gold vector as the only possible equivalent vector. And because I'm the one that made this picture, I can tell you for sure that the gold and the blue vectors are pointing in the exact same direction, and they are the exact same length because I simply copied and pasted them and just changed one of the colors. So equivalent vectors. They have the same length and they have the same direction. Some of your practice problems are going to ask you to sketch vectors, and so let's try a couple and make sure that we get how to do this. Often I've noticed that some of the easier problems can feel more difficult because it feels too easy. So let's take a second to do them anyways. We're going to sketch a vector PQ. The name of this vector is telling us which point is the initial point and which point is the terminal point. So in this notation, we can see that P is the initial point and Q is the terminal point. If we accidentally read this backwards, and we make Q the initial point, P the terminal point, then our vector is going to point in the wrong direction. So it's really important to keep track of who is the starting point and who is the finishing point. Our initial point is P. It's at the location 1, 1. I've got a little graph here made for us on the screen, a little grid. I'm going to plot the point 1, 1. So x is 1, y is 1. That point would go right here. That's our point. And then I'm going to plot the terminal point, the point Q. That's at 8, 5. So 1, 2, 3, 4, 5, 6, 7, 8, and then up 5. 1, 2, 3, 4, 5. And then I'm going to connect the two with the straightest, most perfect line you've ever seen in your life. That's not bad. I'm getting pretty good at this, but normally I draw terrible lines on this tablet. That's all right. We're improving. And I shouldn't have, you know what? Let's redo that. I should not start my line outside of the point P. Although that was a nice straight line, it needs to go from this point and stop at that point. So we cannot extend beyond the initial and terminal points. So when we draw our vectors, make sure that we don't think we're drawing a line and continue outside of our initial point or our terminal point. All right, let's try another one. This vector, ST, the initial point is S. Let's plot that one first at 3, negative 1. 1, 2, 3, negative 1. That's the point S. And then the terminal point, since that letter shows up second in our notation, we know T is the terminal point. That's at the location negative 2, 1, 2, positive 3, 1, 2, 3. That's the point T. And again, the straightest line you've ever seen, boom. Starting at S, stopping at T, not going outside of those 2 points. So we have a new notation, that's our vector notation, where we name the vector using the initial point and the terminal point, and then we put a little arrow above it. So that's one of our vector notations. One of the operations that we'll use often with vectors is scalar multiplication. Now, a scalar is not a vector. A scalar is a regular number. We've worked with scalars most of our lives. So the number 2, that's a scalar. The number 1/2, that's a scalar. The number pi, that's a scalar. Negatives, fractions, decimals, whole numbers, whatever. All regular numbers are scalars. Vectors, however, are not scalars. So note to self, vectors are not scalars. Scalars are not vectors. We have them named different things. Well, because they're different. Scalar multiplication is when you take a number and you multiply it to a vector. So I'm writing this as A, where A is some number, times V, where V is some vector. I'm going to show you what that means visually. So here I have the vector V. If I wanted to multiply V by 1/2, I'm not changing the direction of V, I'm just shrinking the magnitude of it. So scalar multiplication does not change the direction of a vector. So we see that scalar multiplication is not changing the direction, it's changing the magnitude or the length of the vector. If I wanted to multiply the vector V by 2, then I would create a vector that's parallel to V but twice as long. But then I do have this one special case. When we multiply by a negative number, it does flip the direction of the vector around. So when I say that scalar multiplication does not change the direction of a vector, I mean that it doesn't rotate it. It can flip it and completely switch the initial and terminal points, but it can't rotate it. So multiplying by a negative will change the direction of your vector. Otherwise, scalar multiplication only changes the length of your vector. We might also like to add two vectors together. So at this point, we only have talked about the visual representation of vectors, and so that's how I'm going to show you vector addition for now. We will get into the actual mathematical operations later, but let's start with the foundations. So I have two vectors on the screen. One of the vectors is called v, the other vector is called u. If I want to add these two vectors together, what we're going to do is move the vectors. We're going to take the vector u, for example, and move it to where it is tip to tail with v. So when I say tip to tail, I mean the tip of the vector v is touching the tail of the vector u. So we've made a copy of u and moved it up here. Now, this yellow vector that I just created is a copy of the vector u. It has the same magnitude and the same direction. It's an equivalent vector. When I place it like this, I can then create the sum by looking at the initial point of the vector v, following through the tip-to-tail connection, and then continuing on to the terminal point of the copy of the vector u. And then I would create this long red vector, which is the sum of v and u. So vector sum, we do a tip-to-tail arrangement and then connect the first tail to the last tip. For vector subtraction, we technically use vector addition to come up with this shortcut. So again, we're going to go through the visual here. I have the same vectors v and u, but this time I want to find the vector difference, the vector v minus the vector u. The way that we're going to do that is rewrite the vector difference as an addition of two vectors, but we're going to multiply the vector u by a scalar -1. That's going to flip u around. So it does look like we're adding, but we're adding with a backwards u. So we flip u, make a copy, and then we're going to treat this like it's an addition problem. So I'm going to add v with this yellow vector. I need to do tip-to-tail arrangement, so the tip of v is touching the tail of my -u vector. And then, just like we did before, we're going to create a vector that goes from the initial point of v through the tip-to-tail connection all the way to the terminal point of u. And the red vector would be our vector difference. Now, something that's kind of neat about both of these visualizations is that we're creating parallelograms. And we can use these to help remind ourselves what it looks like when we add two vectors together or when we do vector subtraction. So in vector addition, we did tip to tail and then connected the original tip to the new tail. Sorry, I said those backwards. Connected the initial point to the new tail. In vector difference, if we have our two vectors that we're finding the difference between connected, sharing the same initial point, then we can draw a third vector that goes tip to tip. Now, this can get a little bit tricky because if we just think about drawing a vector that connects the two terminal points of u and v, we might get confused about which part of this red vector is the terminal point. Should it be this side or should it be this side? If you go through the process of multiplying u by -1 and then working it out with addition, you'll find it correctly. But if you want to use the shortcut where you just connect the tips, then you have to make sure to remember that the difference vector should always point in the direction of the vector that you are subtracting from. So if it's -u, then I need to make sure to point my vector towards v. Let's look at combining two vectors, again just using our visuals. So I have two vectors on the screen, v and w, and we are asked to create the new vector 3v. So what we're going to do is essentially make a copy of this vector v and then make it 3 units long. So this is a rough sketch. This is not going to be perfect, but that looks about V to me. And then we're going to make it 3 times as long. So our new vector, 3v, would be this guy. What if we wanted to use the same v and w but create v plus w? Well, the first thing I need to do is arrange my vectors so that they have the right orientation. Addition, we said tip to tail. So I'm going to make a copy of w so that this tail is touching the tip of v. Trying to make my best copy of w right there. And then for my final answer, the vector that comes from adding these two together, I start at the initial point from v and I go all the way over to the terminal point of w. And that would be our answer for that one. We can do multiple operations even. So this one asks for 2v minus w. In order to do that, I first need to make a 2. So if this is v, then we could imagine that it's twice as long but parallel. Look at that beautiful straight line. That's 2v. And then I want to subtract w from that. So to subtract w, I'm going to flip it around. I'm going to do it the long way first. And then I'm going to pretend like I'm adding the blue and the yellow vectors. So then I'll copy that minus w down here. Make my final vector from the tip of 2v down to the opposite of w. So that would be 2v minus w. If we wanted to do the shortcut, then I would take w and 2v, and I would align them to where they have the same initial point. This is just a rough sketch, doesn't have to be perfect here. And then I would do the tip to tip vector to do the vector subtraction. And remember, I want it to point in the direction of the vector that I'm subtracting from. So 2v minus w means I need it to point towards the 2v. So I know that the tip of the 2v vector is my new terminal point, which means when I connect tip to tip, it should look this way. Now, shortcuts can be nice, but often it's easy to get them confused. So if you feel confused by this short version, go back and do the long way. Build it up step by step until you feel confident with your answer, and then try the shortcut again. Being able to compare vectors and determine if they are equivalent is very useful. So let's practice that. Here I have the vector v with an initial point from 3 to 2, a terminal point 7, 2, and then w has an initial point 1, -4, terminal point 1, 0. So what we need to do is graph these vectors, because at this point that's all we've learned how to work with, and then we can compare to see if they're equivalent. So we have the graph on the screen for us to use. I'm going to make some colors here. Let's make the vector v blue. So if I have my x-axis and my y-axis, let's graph our initial point at 3, 2. So 1, 2, 3, up 2. Point for v, terminal point is at 7, 2. So 7, 1, 2, 3, 4, 5, 6, 7, up 2. There we go. There is our vector v. Now let's make the vector w. Same process here. We're going to graph the initial point at 1, -4, and our terminal point at 1, 0. We draw our directed line segment with the arrow at the terminal point. That is our vector w. In order for these vectors to be equivalent, they need to have two things in common. They need to both be pointing in the same direction, and they both need to be the same length. Now, I can tell they're the same length but I can also tell that they're not pointing in the same direction. So not equivalent, different directions. Let's try another set of vectors. This time we're plotting a vector at 0, 0, pointing to 1, 1, and also a vector at -2, +2. Oh, I want to change colors there. Pointing to -1, 3. So now comparing the blue and the purple vector, they look like they are pointing in the same direction. If we thought about a slope of a line, this looks like they have a slope of 1. And they're the same length. They go diagonal across one square perfectly. Now let's start to talk about the notation for the position vector's component form. A standard position vector is a vector with an initial point at the origin. So the vectors that we had seen before, maybe the initial point was not at the origin. Maybe it was, but if the initial point is not at the origin, then we are not talking about a standard position vector. Sorry, yeah, that's right. If we do have the initial point at the origin, then guaranteed standard position vector. The terminal point of any position vector is pointing to a point with the coordinates that match the components of a vector. So let's pause for a second. In this picture, I have the yellow vector and I have the green point. This yellow vector has its initial point at the origin, so I know it's a standard position vector, which means I can look at the coordinates of the terminal point and I can use those to describe the vector in a component form. So whatever x value that this green point has, I would place that in these pointy brackets as the x component of the vector v. Same with the y coordinate of the green point. I would take that value and I would plug it in as the y component of the vector v. If we wanted to write out the component form for the vector that we have drawn, I can see that the green point is at 1, 2, 3, 4. So it has a 4 coordinate and the x coordinate, and then it has a 3 for the y. It's up 3 units. So this would be the point, or the terminal point rather. And once I know what the terminal point is, then I can write the vector in component form. We write the name of the vector, so rather than writing initial point, initial point then terminal point, I'll just write the name of the vector, which is v, with a little arrow on top, and then I would say that that's equal to the components. So I use pointy brackets, not round parentheses, and I would put the same x value as the coordinate of the terminal point, and then I would put the same y value as the coordinate from the terminal point. And that would be our standard position vector in component form. Now something that's kind of neat is that I can copy this vector v and make it not a standard position vector. For example, I can create my initial point here, and I can use the coordinates 4, 3 to help find the terminal point from my new initial point. So I would go 4 in the x direction and up 3 in the y direction. And that would be my terminal point. So this blue vector that I've drawn, it's equivalent to v, but it is not a position vector because this initial point is not at the origin. Now that we know what component form is for a position vector, we can take a vector that's maybe not in standard position. We can rewrite it in component form using just a small little formula. So on the screen I have a vector v, and if I let this be the x-axis, this be the y-axis, our initial point looks like it's at 1, 2, 3, 4, 5, 6, 7, and up 1, 2. So our initial point is at 7, 3. Our terminal point would be at 9, 9. So our initial point and our terminal point, I'm able to identify that here. I can tell this is not a position vector because my initial point is at 7, 3, not at the origin, but we can create a position vector just by finding out what the change in x is as well as what the change in y is. So looking at the change in x from the initial point to the terminal point, we have 2 units. And we can do subtraction to find that if we'd like. Subtract the terminal point's x value from the initial point's y value. So that would be 9 minus 7 to get the 2 units that we see here. We can do the same thing with the y components. From the initial point all the way up to the terminal point, we have a vertical change of 6 units. And we can do that mathematically. Take the y component of the terminal point, which is 9, subtract the y component of the initial point, which is 3, to get 6. And that's all that this formula is saying. If you want to create a vector in component form, where you know the initial point and you know the terminal point, then you just find the change in the x values as well as the change in the y values. The part I want to draw your attention to is that you need to have the terminal point coordinates first when you do the subtraction. So it's terminal minus initial for the x part, terminal minus initial for the y part. If you get those backwards, you will have a sign error in your components. So let's try some of these examples where we don't have a picture in front of us. Initial point at -3, 4, and a terminal point at 1, 2. If I want to write this in component form, then I'm looking to write this using brackets. I need the change in x values. Terminal point has an x value of 1. So I do 1 minus the initial point x value of -3. Careful with your negatives here. And then I need to do the same thing for the y values. So terminal point has a y component of 2. Initial point has a y coordinate of 4. So we have 2 minus 4. And then we can subtract those. 1 minus -3. That gives us +4. 2 minus 4. That's a +2. So the component form for the vector with an initial point at -3, 4 and a terminal point at 1, 2. Component form is in pointy brackets 4, 2. Let's do one more real fast. This vector w has an initial point at -4, 5 and a terminal point at -1, 2. So to calculate the components, I'll do -1 minus -4 and then 2 minus 5. Simplify that down so we get 3, -3. Now that we've learned how to describe vectors without pictures using components, we might also want to talk about the magnitude of a vector without talking about how long an arrow is. The magnitude of a vector v has 2 different types of notations. We can use the double bar notations, or we can use the single bar notation. Now, I hear this every semester. I don't like using the single bar because it makes me think of absolute value. Well, what I say to that is, throughout this entire semester, you're going to see a notation that you've used time and time again, but never used it on a vector. When you put these bars on a vector, it doesn't necessarily say absolute value, but it kind of does. Absolute value just asks you to find how far away from 0 you are, and the magnitude of a vector is finding a distance as well. So you really could look at this as an absolute value if you'd like, or you can look at these absolute value bars as if they were the magnitude of a scalar. So it's just another distance question. If you'd like to use the double bars, that's fine. I'm going to use the single bars because it's less writing and sometimes I get lazy. So when we have this notation, vertical bar, vector v, vertical bar, that's saying magnitude. If we want to talk about the magnitude of a vector, we're going to bring it back to good old Pythagorean theorem. I have a vector here on the screen, and you can tell that the initial point is at the origin, so we know that this is a standard position vector, which if I wanted to write this in component form, I just need to locate the terminal point coordinates. This terminal point is at 2, 5. If I wanted to find the magnitude of a vector that's at a position vector at 2, 5, all I need to do is think about a triangle. So if I made a right triangle with the x-axis here, and I know that the bottom side is 2 units long, the right side is 5 units long, then I could use the Pythagorean theorem to solve for the hypotenuse. So I would say something like 2 squared plus 5 squared equals c squared. Solve for c. I need to take the square root of both sides. And c would represent the magnitude of the vector. Well, that's exactly what this formula is telling us to do. Take the x component, square it. Take the y component, square it. Add those together, square root, and you've got your magnitude. So if I'm looking at a vector v with components 2 and 5, then I would write that as 2 squared plus 5 squared, square root it, and simplify. So we have 4 plus 25 square rooted, or the square root of 29. Now I will always get this question, is it okay to leave it as the square root of 29? Should I switch it into a decimal? Should I try and simplify to the reduced form of this square root? The answer will always say, it depends on what you need to do with it. If you need to have an intuition about how large this number is, square root of 29, then maybe you should turn it into a decimal. And if you turned it into a decimal, it would look like about 5.4 units. If you wanted to use this magnitude as part of an equation, then maybe you should use the exact form, square root of 29. Something that we kind of take for granted is that y'all have been studying math for a long time, and you should know the difference between an approximation, where we rounded off our decimal, and an exact form. If I ask you for an exact form, then I do not want you to give me a rounded decimal. I need you to give me the exact form, which would be square root of 29. If I want you to approximate, then you can round your decimals, and then I might even tell you how many decimals to keep. But let's make sure we know the difference between exact and approximate answers. Continuing to work on the same slide, I've erased all of the ink so that we can do the problems that are listed here. We want v to be a vector with the initial point of 2, 5 and a terminal point of 13. If I want to find the magnitude of this vector, then the first thing I need to do is find the components. So to do the components, remember we find the change in x and the change in y. So v will look like 13 minus 5 and 8 minus 2. So our x component would be 8, our y component would be 6. Those are the components. Then step 2 would be use the formula, square each of the components, add them together, and square root them. let's take a look at doing some operations in component form. We know how to add vectors visually, but now that we know how to work with vectors using components, let's try it as well. If I'm adding the vector v to the vector w, I'm going to add component by component. So v plus w is going to look like 6 plus negative 2 for the x's, 8 plus 4 for the y values. So we'd have 4, 12. If I wanted to do scalar multiplication using the components, 3 times the vector v is going to look like 3 times the components of v, which are 6 and 8. And really, we distribute that scalar to each component in our vector. So that would become 18, 24. One more here, v minus 2w. So I'm going to write this out in component form. Here's my vector v minus 2 times my vector w. We kind of have to do order of operations here. We're going to multiply the scalar into the vector w first, so that we have minus the vector 2w, which would be negative 4, 8, copying down v. And now we're going to subtract the components. So we have 6 minus negative 4 for the x components, 8 minus 8 for the y components, or 10, 0 for our final answer. We've got some properties to talk about with vector operations. First one is addition is commutative. Notice that on the left side of the equal sign we have u plus v. On the right side we've changed the order. So this is true for addition of scalars and for vectors. Next we have the associative property. This says that you can change the grouping when adding 3 or more vectors, and the answer will come out to be the same. Next we have the zero vector. This is not a scalar, this is a vector. I know that because it's got an arrow on top. When you add the vector u to the vector 0, you get the u right back. So zero vector is like the identity for addition. And then next we can see that we have the additive inverse. So the vector u plus the opposite of u should give me the 0 vector back. These are all properties we've seen before. We just want to make sure that we understand that they apply to vectors as well. For multiplication, multiplying by the number 0, the scalar 0, creates the 0 vector. Multiplying by the scalar 1 is like the identity for multiplication. It returns the vector u. We also have that scalar multiplication is associative. So I can multiply u by the scalar b first and then the scalar a. Or I could multiply the two scalars, a and b, together, then to the vector u. So scalar multiplication is associative. This next line says that we can take a scalar, like a, and we can distribute it over vector addition. The next one says that we can take the sum of two scalars, and we can distribute that to scalar multiplication. So I could do a times u plus b times u, like we have on the right-hand side, or I can add the a and the b together, then multiply that sum to the vector u. So these are just some properties that we're going to use from time to time. Wanted to make sure that we saw those.